So in this session, we're going to look at some sample two-phase flow systems, basic enough two-phase flow systems. And we're going to just look at the different approaches you can take to modeling these types of systems. But before we do so, we'll just show you if we select Options, Calculation, and select the two-phase tab. Obviously, we've got gas and non-Newtonian, settling, slurry, pulp and paper stock calculation settings. But if we look at the two-phase option, we've got the drop-down menu, and you can see the correlations that you can choose from when you want to model your system. So I'm just going to use the Wally criteria, in which case the software analyzes the fluid physical properties and applies the appropriate correlation. Okay, so let me just cancel that. I'm just going to use that Wally criteria. So the first approach you can take, now there's three, but the first approach you can take is changing quality. Second approach is constant quality, and the third approach is simply to define pressure and temperature and allow the software to automatically track fluid phase state throughout the system. Now the software always automatically tracks fluid phase state, which we will see as we work through a number of models. So let's start by building this changing quality system. So I'm just going to place a boundary element on the screen like so, and I'll have a horizontal pipe, and then we might have an incline like so, and then I'll drop it back down and come back to the end like so. Okay, and what I'm going to do is I'm going to insert a heat exchanger into this point of the system. So let's insert a plate heat exchanger at this location. Now let's assign the appropriate fluid at the boundary. In this case, we're going to have R152A like so, and the pressure we will set it to 1.16 atmospheres, and what we'll do is we will we'll define the quality. So we set the fluid type to two-phase, and now it's asking us, okay, so what's the quality? And this is an approach which is often used in steam systems, where you may know the steam quality in your system. But I'm just going to set it to 0.18 or 18% vapor quality in this case. Let's now look at the final point is elevation. So you can set elevation for your pipes by choosing a boundary or a fitting. Okay, so I'm just going to set that elevation to 6, and likewise I'm going to set the elevation of this bend to 6 meters. Now the first pipe in the system is just going to be 2 inch, and I'm going to leave it at 10 meters. Then we come to the next pipeline. I'm going to set it to 8 meters, and again I'll leave it at 2 inch. This bend I will set to have an elevation of 12 meters. This pipeline I'll again set to have a length of 8 meters, and I'll leave it at 2 inch once again. The next bend 6 meters, and this pipe I will set to 2 inch and 5 meters. Yeah, plate heat exchanger, then we will set it to have a fixed transfer rate of energy. Okay, and we'll set it to transfer the energy into the network, and it's 30 kilowatts, okay, or 30,000 watts. I'll just leave the rest of this information as default for the moment, or for this demonstration, if you like. Now this pipe I'm going to leave it at 5 meters, and what I'm going to do is I'm going to change some common properties now for the pipes. But let me just look at a few more of these elements. Okay, so this bend I had set to 6 meters elevation. So the heat exchanger I'm going to set to have an elevation of 4 meters, and this bend I will I'll leave it at 0 actually, and I'll leave this bend at 0, and I'll set this one to 4. Okay, so I'm just going to look at pipe lengths firstly. So I'm going to leave that at 5 meters, leave this one at 10 meters, and this vertical pipe I'll also leave at 10 meters. But I want to change all of these 3 pipes to 3 inches. Now by default they're set up on the flow sheet as 2 inch schedule 40. So and that's because I've created this model using the first pipe material available to me using steel pipes here. You can choose from other pipe materials if you wish. So what I'm going to do is I'm going to select the first pipe of interest, hold the shift key, and then I'm going to choose the other pipes. And I'm going to change all of these 3 pipes to 3-inch schedule 40 at once. Okay, so that's it, job done. And what I can do at this stage is calculate. And now you can see the flow direction is shown throughout the model. Now, we knew that the quality was 0.18 or 18% at the inlet of this system. And if I look at the results, you can see that's carried across. So 18% quality. And based on the operating conditions and quality settings, the software has determined the physical properties for our fluid. Okay. And if I look at this first pipeline, you can see it's applied the Friedel correlation. The phase state is 2 phase at the pipe inlet, 18%, which we know. And then we've got the rest of our conditions. And then at the outlet of the pipeline, again, it's in the 2 phase state, but you can see the quality is increased to just 18.3%. Okay, so we've got some flashing occurring in this pipeline due to the pressure drop in the line. So we've got a slight increase in the quality in the system. And that's what happens throughout the system. Okay, and then we get to the point where we have this heat exchanger, and you can see that the quality is increased to 0.19 or 19.6%, but we're adding this 30 kilowatts of heat into the system, and you can see now the quality is increased to 45.7%, and all physical properties, of course, updated accordingly. And that's what happens. So the software automatically tracks phase state and physical properties of your fluid throughout the system. Okay, so another perhaps interesting point is if we look at the chart tab, you can see the friction loss versus flow, but you can also see the flow pattern map. Okay, so you can see we're just on the border of the stratified, wavy and annular mist flow regimes. Okay, so the red dot here denotes the duty point. Now if I look at the next pipeline, you can see we're actually in the annular mist region. Okay, and that's because obviously we've got this inclined pipe, we've got a change in the characteristics, and we've got an increase in the gas superficial velocity as well. So if we look at the first horizontal pipeline, because the elevation, remember, at the inlet and outlet was 6 meters. Okay, so if we look at the results here, you can see that the liquid and gas superficial velocity is shown at both the inlet and outlet of the system. So gas was 7.86, increasing to 8.21. And then if we look at this inclined pipe, the gas superficial velocity is 8.25, increasing to 8.69 meters per second. Okay, so what I'll do now is I'll look at the next option of defining a system using constant quality, but instead I'm going to use a known flow boundary or a fixed flow boundary in this case, and I'm going to just use a connector junction element just to allow me to mix these fluids in the system. And what I'll do is I will place a separator or knockout pot in the system with an outlet condition like so in pressure. Okay, and I'll insert a plate heat exchanger again like so. So I'm going to multi-select once again to change common properties, because I want to change both of these known flow boundaries to have flow going into the network. By default, it's out of the network. So into the network, and obviously if we have fluid going into the network, it asks me now, okay, what's the fluid and what's the temperature? So let's start with the first one. Okay, we'll leave it at water and we'll set it to 25 US gallons per minute, like so, and we'll leave it at, well no, we'll change it to 29 degrees C. And then for the second inlet, we'll set it to 0.08023 kilograms per second, just to show you how you can use different units or unit environments in the one model or the one flow sheet. So we'll set it to 29 degrees C, and we'll change the fluid to air, like so. Okay, now because I'm only using these first pipes, pipe -1 and -2, for connectivity purposes, to allow me to mix these two different fluids at this point, I'm only going to use a very short length of pipe work, okay, and I'll actually ignore pressure loss as well in those lines. So for this pipeline, let's give it a length of 60 meters, and also actually let's give this pipe length of 60. It would help if I could type 60 meters. Okay. Now, just to show you some other feature, I'll hold the shift key and select both of these pipes up and downstream of this heat exchanger. So obviously the nominal size here, if you click the little grey box, it allows you to access the pipe's database and change any pipe size and choose any pipe classification from the database, and you can always add new pipe classifications to the database. But for instance, if you know the inside diameter of the pipeline, what you can do is you can say, no, I don't want to use the inside or I don't want to use the pipe's database. I want to define the inside diameter of my pipe. So that's what I'm going to do here. I'm going to say it's 50.8 millimeters. And then I get to the heat exchanger, and I'm going to base this time the heat transfer on fixed temperature change into the network, and I'm going to set the temperature change to 30 degrees C. So by setting the temperature change, the software calculates the resultant energy transfer, and likewise if I had defined, like the first model we looked at there, the amount of energy transferred, the software calculates the temperature change. Okay, and you can view that information in the results. Again, I'm going to just retain the default pressure loss model and data for this heat exchanger. I'm not really too concerned or interested in that at the moment. So I am going to set the vapor outlet to pipe -3, which is this top pipeline. So there we can see the yellow dot is positioned at pipe -3, and now the liquid outlet is going to be this red dot, which is this outlet point down here. So that's all I'm going to set up for the knockout pot for the moment. This pipeline, I'm going to set it to 6-inch schedule 40 and give it a length of 5 meters. And I'm just going to leave the outlet of that pipeline at 1 atmosphere. Likewise, I'm going to leave the outlet of this line, this liquid line, as 1 atmosphere pressure. And I'm just going to leave these lengths and diameters as 10 meters and 2-inch for the moment. Okay, so let's calculate the system. Now, because we have defined, a fixed flow rate of water entering the system at this point and a fixed flow rate of air entering at this point, we have fixed the mass flow rate of these fluids entering the system. So in doing so, we're fixing the quality in the system, so it becomes a constant quality system. So if we now look at the vapor quality at the inlet of this first pipeline where we have fluid mixing, you can see it's 0.048, and likewise at the outlet is 0.048, and that's what's carried right through the system, 0.048 at the outlet, 0.048 at the inlet of this pipeline as well. But all the other physical properties of the fluid are calculated accordingly. So you can see, for instance, the instagnation temperature is 29 degrees C, increasing to 59 degrees C because we're adding the 30 degrees C of heat, and you can see then the level of heat transferred in watts. Now you can change any of these units. So for instance, I can change heat transfer from watts to kilowatts, like so. So you can see we have 181 kilowatts of heat transfer. It's a two-phase system, obviously. And if we look at the first pipeline, remember, this pipe has a length of 60 meters and is 50.8 millimeters in diameter, and likewise the downstream pipe 60 meters in length with a diameter of 50.8 millimeters. So this pipe and this pipe, -6 and -7, are identical. But if we look at the results for this first pipeline, you can see the friction loss is 114,000 pascals, thereabouts, just over. And if we look at this line, it's a little bit higher. Why is that? And that's because obviously we've got the change in fluid physical properties occurring. We've got the increase in gas superficial velocity from 15 to 36 meters per second. So what you'll notice is the acceleration loss has been taken into account in the system, and hence the higher pressure drop value in the downstream pipeline. Then we get to this knockout pot where we have vapor being taken off the top. So we've got gas or vapor phase, and then we've got the liquid phase coming out the bottom of the separator or knockout pot. Okay, so we've got constant quality in this system. Let's look at the third or final approach you can take. What I'll do is I'll just place two pressure boundaries on the flow sheet like so, and connect them together and insert a pressure control valve like so. And what I'll do is I will set the pressure to 2 atmospheres and 120 degrees C water, and I leave the downstream condition at 1 atmosphere pressure. I'm going to leave the automatically size function off. So basically in FluidFlow you can automatically size flow control valves, pressure control valves, pipes, orifice plates, relief valves to API and ISO standards. You know, the list goes on. Nozzles, venturi, tube. You can automatically size your pumps and fans and so on. You know, centrifugal pumps, PD pumps and so on. But I'm just going to leave this function turned off, and I'm going to set the design pressure to 120,000 pascals absolute. So you've got pascals gauge and pascals absolute. I'm going to choose absolute. You can choose your measurement type, so stagnation or static pressure. Measurement location up or downstream. I'm going to leave it as downstream in the valve model. In this case, I'm just going to leave it as the 2-inch butterfly valve. But if you wanted to change it to another valve from the database, you just click the grey box to access the database and choose the relevant valve manufacturer, and then, for instance, under Keystone, you know, choose the particular valve of interest. And again, you can add your own valve data to the database. So the final thing is to define the input information for the pipe. So again, I'm going to multi-select and select the length of both pipes as 10 meters, and I'll just make sure, yeah, I'll leave them as 10-inch schedule 40. So I'll calculate the model. Now we've got a warning message for the valve. Okay, so it's telling us that we've got a design condition that we might want to review. So the valve duty point is less than the minimum limit. So we've got a minimum limit setting in the software, which you can edit or change based on your design preferences. And basically, if I look at the results for this valve, it's telling me the valve position is just 16% open. So not really an ideal design operating condition. Okay, so at least you're getting a warning message now to prompt you into reviewing this. Okay, so the minimum limit, for instance, if I select warnings and hints here, you can see you've got different conditions for liquids. So if you're below the minimum limit for your control valve of 20%, which we are 16%, you'll get a warning message enunciated. Okay, so you can see we're actually in liquid phase at the inlet of this control valve, and hence the warnings enunciated based on this 20% value. So but what we're just showing you here is that the software has automatically tracked fluid phase state throughout the system. So we're flashing from liquid across the control valve into the 2-phase state, and then the vapor quality and so on is shown for us. So by defining the pressure and the temperature, the software then automatically tracks fluid phase state. So we're in liquid phase and 2-phase at the downstream side of the control valve. So that's just a very quick overview of the 3 different approaches you can take. So remember, changing quality, where you set the quality of the fluid, vapor quality, at the inlet of the system, and the software solves on that basis. The second approach, constant quality, where you define a fixed flow of, you know, a liquid or a gas entering the system, and the software solves on that basis. And the third, where you define the pressure and temperature, and then again the software solves on that basis. So what we'll do is we'll just look at a very quickly look at a few sample systems. So this is a geothermal system where we have a number of wellheads collecting steam in the system. So we've got 24% vapor quality, 20%, and so on. And you can see some of these elements are turned off, okay, so they're not taken into account in the calculated solution, but you can turn them back on at the status field if you wish. So you've got separating occurring. We've got high, intermediate and low pressure conditions in this particular system, and the pipes are highlighted in red and orange and green to help denote that. Okay, so we've got LP, low pressure, intermediate pressure, IP, and the higher pressure condition at the top. Let's look at another sample system. So this is just a very basic sample refrigeration circuit. Okay, so we've got R134A assigned to the system. We've got adiabatic compression taken into account, and then we're adding, we're removing 348 kilowatts of heat from the system. So you can see we have fluid and gas phase right up to this point where we have the heat exchanger, and then we change from gas phase to liquid phase, and we're in liquid phase throughout the system to the point where we get to this pressure control valve controlling the entry static pressure at 8.5 bar absolute. Okay, so we flash then from liquid to two phase. So we've got two phase now passing through to this heat exchanger where we're then adding 300 kilowatts of heat back into the system, and we go from two phase then back to gas or vapor phase. So you can see the phase state is automatically tracked for us throughout this particular network, and this network is just basically set up to demonstrate that specific feature. The last network we'll just look at here very quickly is really just showing us how we can mix different fluids. Okay, so we've got a mixture, two-phase mixture entering the system. Okay, and we've also got heat transfer taken into account in the pipelines. 39 meters of 8-inch pipe in this first case. Then we're adding a gas, okay, methanol in its gas state. So we've got mixing occurring at this connector point, or this junction. Then we're adding a liquid. Then we're adding another single phase fluid, water in this case. So we're continuously mixing these different fluids throughout the system. Then we're adding nitrogen and water at this point, and you can see you've got the percentage composition of each of these fluids in each of the pipes. So you can see water, aniline, methanol, with the addition of the nitrogen in the final pipe, and the composition is analysed and updated throughout the network as we proceed and mix or add these different fluid mixtures to the system. So that's really a basic and brief overview of some of the two-phase networks and different approaches you can take to modelling your two-phase system. So if you have any questions, you can always contact us, and you can visit our website fluidflowinfo.com to get some contact data. Okay, thanks for your time.